So let's recap what we've done. Row reduction is the first. So row reduction, then column reduction, then optimality check. If it's optimal, then we could go ahead and go to assignment right away. If it's not, then we have to do step number 4, which is about the uncovering, dealing with the uncovered elements and adding the lowest of those uncovered elements to the intersection point. If we reach optimality of that point, we make assignment. So what happens when we get a maximization problem for Hungarian method? So Hungarian method is designed for a minimization problem. So it is not designed for a maximization problem. So when we get a maximization problem, we need to do something a little bit, something extra, which is going to be taking the highest element in this table, the whole table. And it happens to be 21 in this case. And we're going to subtract each element from 21. So here 21 minus 5, it's going to give us 16. 21 minus 12 is going to give us 9. So the highest element number is going to be basically the number used to subtract each element from to get a new number. And once we do this, we get a new table, and that new table, we're just going to apply the procedure we talked about. So we're going to treat it as if it's a minimization problem. That's how we get around a maximization problem. We just turn it into a minimization problem, and then we follow the Hungarian method minimization procedure. That's all there is to it. So in sequencing, there is another very important topic, which is Johnson's rules, which is basically trying to assign jobs to machines or work centers. And we have some conditions that we need to respect when we do this. So the jobs must be known. Jobs must be independent of the sequence. That's another very important assumption. They must follow a two-step sequence. So they only work, these Johnson rule only works for two job sequence. All units must be completed in the first work center before moving to the second. So you can't, if something is not complete in the first work center, it cannot be moved to the second, which is common sense. And there's enough space for work in process because we're going to have some work in process. So these are the main assumption for the Johnson's rule. So in here, what we're going to do, we're going to list the jobs and their times for each work centers. As we said, we're only going to have 2 work centers because that's what Johnson's rule only works for 2 work centers. So we're going to have work center 1 and work center 2. And we're going to select the jobs with the shortest time. So we're going to have jobs, and if the shortest time happens to be in the first work center, we're going to schedule it first. It happens to be in the second work center, we're going to schedule it last. And then those jobs, we'll eliminate them from further consideration, and we keep doing this till all the jobs are scheduled. So in this case, again, we'll follow the rule. So this is Johnson rule, and we have 5 jobs, which is fine. And we have 2 work centers, which is exactly what the Johnson rule requires, that we have 2 work centers or 2 machines. And we're going to pick the lowest number in this whole table, which happens to be 4. And because it happens in the second work center, we're going to schedule it last. So we're going to schedule job A last because it happens to be in the second, the lowest number happens to be in the second work center. So we're going to schedule it last, and we're going to cross out this job because we cannot schedule it, and we've already scheduled it. Then we go on to find the next lowest number, which happens to be in this the remaining number in the table. 6 happens to be the smallest, and that 6 happens to be in the first work center, and it happens to be job B. So we're gonna schedule job B first. So job B first because it happens to be in the first work center. We cross out these two, and we remain with 6 numbers. We take the lowest of that, which of all these numbers, which happen to be 7, and then select the job with the shortest times. That happens to be 7, and it's in the second work center, and we're gonna schedule it last because it happens in the work center. We already scheduled something last, so it's gonna be the one before last because we already scheduled the last spot. So C, because the job happens to C, is going to be the one before the last. Now we're left out with D and E. Now the lowest is 10, but it is in both rows, so it doesn't matter. We could pick randomly, whichever we want. So we calculate, we take E, and E, this 10 happens to be in the first work center, so E is going to be the remaining first. So out of the remaining spots, the remaining first spot is going to be E. Now from there on, we know that D has to go here because that's the only activity job left. And that's basically Johnson's rule. It's quite simple. Just have to remember 2 work centers. The first work center, if the minimum number happens to be in the first work center, then it's going to go first. If it happens to be in the second work center, it's going to be last. If we have some of the spots populated, then it's going to be the last available spot or the first available spot for work center 1. So determining the make span. So some question might ask us to do Johnson rule and then determine the make span. And basically what that make span mean is how long does the process of all the jobs into work center 1 and work center 2 take. So we start with the our BEDCA. We know that B will take on the first work center is going to take 5. Here they're telling us it is in hours. So it's going to take 5 hours. Then we have E, which happens to be 9, and we say 9 plus 5, it's going to be 14. So far 14 hours. Then D takes 12 hours. 12 plus 14, we got 26 hours. C happens to be 10 hours. 26 plus 3 is 36. Then finally, A happens to be 7 hours. 36 plus 7 is 43. Now, very important when we go to work center 2, work center 2 cannot start B until B is done from work center 1. So it's going to wait till the 5th hour for it to start because it's waiting for B. And then we're basically going to schedule B. And now we're using the times we got from the work center, the second work center. So B happens to be 8. 5 plus 8 is equal to 13. Now here we cannot start E at 13 because E is being still processed in work center 1. So we have to wait for 14 till E is done. Then we're going to start at 14 and E is going to take 14 hours. So 14 plus 14 is 28. Then D is going to take 9. 28 plus 9 is 37. Then we have C, which will take 6. 37 plus 6 is going to be 43. And then finally, A is 7. 43 plus, A happens to be 4 for work center 2. So 43 plus 4 is going to give us 47. So the total make span is 47 hours. And we have to do it step by step because we have to realize that there's going to be some idle time. So 47 hours, the total idle time is going to be the idle time here, which is 5 hours. And then there's the 1 hour we're waiting for E to finish, so it is going to be 6 hours in total. So that basically concludes the Hungarian method and Johnson's rule. Our next videos are going to be on the process re-engineering. So I'll see you in the next videos.